All right, time for exam one. Let's go through some problems. So the format of the exam will look a lot like this, starting with some multiple choice questions worth just a few points each. First one, how many milliliters is in 0.05 liters? However you have, worked on this, you can do it. There is an equation sheet that has the prefixes on it, but this is one I would probably just memorize. Either I can move the decimal 3 places to the right, or I can multiply it by 1,000. There's 1,000 milliliters in 1 liter, and either way, I get 5 milliliters. Now, the next one is similar, except there's a couple of things. For one, I'm going all the way from centimeters to kilometers, and so through the base unit and beyond, I'll sort of break it up into steps. But also, because of the squared, I need to consider that. So let me just show you what I mean. 28.5 centimeters squared. I know off the top of my head that there's 100 centimeters in a meter. That's one that I've memorized. Again, you could use the equation sheet prefixes to do that. And I also know that in 1 meter, there's, in 1 kilometer, there's 1,000 meters. And so that would get me all the way from centimeters to kilometers. But because this is squared, I have to square these. So basically, this is like saying, this is centimeters times centimeters. And so this is going to be centimeters times centimeters to give me meters times meters. I have to do it twice to do that. So I'm going to do it like this. All right, so 28.5 divided by, I'm going to do it in steps just to make sure everything ends up in the right place. So 100 squared, and then divided by 1,000 squared. I have a super tiny number. I only see a 3. That's not good. That doesn't match any of my answers. That's dropping a bunch of sig figs. So I'm going to convert this to scientific notation. And I see I don't even have to count those zeros. 2.85 times 10 to the minus 9. Significant figures. Remember, anything that's not a 0 is significant. A 0 in the middle of non-zero digits is significant, and a 0 at the end of the decimal is significant. All right, aluminum, 3+. So let me just think about, hold on, I'm grabbing my periodic table here. Whoops, knocking things down. Aluminum, 13. That's how many protons it has. An aluminum atom would have 13 protons and 13 electrons. An aluminum 3+ ion has to have 3 extra protons. So it has to be missing 3 electrons. Okay, the next one is just this to me is a definition problem. Which of the following is an ion? I have to know what an ion is in order to answer it. And it's A. An ion is something that has a charge, right? So the boron with a charge. This NaCl is an ionic compound. Helium all by itself, I would call that probably an atom. And this one where it shows the specific mass number would be probably an isotope. Would be probably what I would be looking for those. All right, how many of each type of atoms does a compound of? Okay, so that's 3 lead. That didn't narrow it down. And then 2 phosphorus, 8 oxygen. Right, that 2 gets multiplied through. All right, which is colder, 20 degrees Celsius or 40 degrees Fahrenheit? I have no idea, right? I don't know. I do know that if I have them in the same unit, that I can compare them. So let me put one of them in the same unit as the other. I don't have the equations memorized for how to convert, so I can pull out my equation sheet. I could go either way. I'm just going to use this first one here. So to figure out degrees Celsius, it'll be the degrees Fahrenheit minus 32 times 5 over 9. I'm copying that off of the equation sheet. So that means I'm going to take my 40 Fahrenheit, subtract 32, turn it back to not scientific notation, times 5 divided by 9. And that would give me 4 degrees Celsius. So 4 degrees Celsius or 20 degrees Celsius, which is colder, it would be 4 degrees Celsius, which is 40 Fahrenheit. I could do it the other way too, just for the record. If I wanted to use the other one, I'm looking again at my equation sheet, and it says degrees Fahrenheit would be 9 over 5 times Celsius, and then add 32. Let me just do that for good measure. 9 over 5 times 20 plus 32. I wanted to put it in, I just want to make sure I got it in there correctly. So I want 9 on top, 20 on top, and 5 on the bottom, and then plus 32. Would be 68 degrees Fahrenheit, so still 40 is colder. So it doesn't matter which way I go, I should get the same answer. Okay, which of these pairs of elements is most likely to form an ionic compound? So when I'm doing this, I want a metal with a nonmetal. So here I see a nonmetal with a nonmetal. Nope. A metal and a metal. Let me just grab my periodic table so you know what I'm saying. All right, so chlorine and iodine are both over here in the nonmetals. Potassium and aluminum, there we go, are both metals. That can't be it. Chlorine and magnesium, that looks pretty good. Magnesium and chlorine, okay, that looks like a metal and a nonmetal. That looks pretty good. Carbon and sulfur, all right, those are both way over here in the nonmetal section. That's not so good. Aluminum and magnesium, we've talked about those both already. They're both metals. So the only one I see where I have one metal and one nonmetal would be C. The ground state atom of manganese has this many unpaired electrons, and it is. Okay, so I need to do the electron configuration of manganese, which is Mn, right here. So I can start with argon. Argon. One, two, 4s2, and then 1, 2, 3, 4, 5. So this would be one line with 2 electrons. This would be 5 lines. Remember, D always gets 5. 1, 2, 3, 4, 5. 5 unpaired electrons. Remember, paramagnetic means there's at least 1 unpaired electron, so 5 unpaired electrons makes it definitely paramagnetic, but that was my only choice if I have 5 unpaired. All right, and then everyone's favorite, which one of the following sets of quantum numbers is not possible? So I'm going to go down the columns and check them one by one, however you want to do it, right? You could do across if you want. But for n, I know 1 is the smallest it could be, can't be negative, can't be decimals, those all look fine. L can be 0, and it could be a maximum of n minus 1. So this could be a maximum of 3, maximum of 2, maximum of 2, maximum of 1, maximum of 1. Those are all fine. Then looking at my m sub L, it can go anywhere from negative L up to positive L, so negative 2 is fine. 1 is not, because it can only be 0. 0 is fine, 1's fine, 0 is fine. M sub S plus or minus 1/2, so this is the only one with a problem. All right, now let's do some electron configurations. So hard to pull my periodic table out too much for this, but I'm going to put these all in noble gas configuration, but you don't have to. So I'm going to put helium and then 2s2, 2p1, 2, 3, 4. If you wrote that as 1s2, 2s2, 2p4, either one of those would be totally fine. I'm just going to jump ahead. I see O2 minus here. Since I just did oxygen, let me just think about that. 2 extra electrons would go all the way to being isoelectronic with neon. So I could put that for my answer. Or I could put that as my answer. All right, vanadium is right here. So it would be argon 2s2. No. Argon 4s2. And then remember, this is down by 1. So 3d, 1, 2, 3. Jumping down here to my ion of vanadium, it would be argon. And now I have to lose 3 electrons this time. And remember, for transition metals, they come from the S first. So my S2s would be, my 2 S's would be gone, and 1 of my D's. All I would have left, I had 5, I took away 3, and they would both be D's. And then molybdenum is right here. Would be krypton, 5s2, 4d, 1, 2, 3, 4. Now, this is an exception. Depending on which class you're in, I may have told you to memorize this, and it's an exception. Maybe not. So maybe you put this. The exceptions I for sure want you to know are chromium and copper. If it was chromium, it would be just like this, except it would be like 4s and 3d. But it's to half fill that D subshell. For this one, either one of those I think is fine. I think this semester I asked you just to memorize chromium and copper. Okay, and since we have these electron configurations, drawing the orbital diagrams will be a piece of cake. Helium. I look back up here, I had 2s2, 2p4. So 1, 2, 1, 2, 3, 4. And then for vanadium, S2, D3, like that. All right, up next, naming compounds. So I have 5 compounds here that I'm going to name. One of them does not have any metals in it, so that's a molecular compound. The rest all, sorry about the focus here, hold on. All right, hopefully that'll work. The rest all have a metal in them, so if the metal, grab my periodic table again here. If the metal has a for sure charge, like barium is a +2 all the time, then it's just barium. Change the oxygen to an IDE ending, oxide. If it's something that has multiple possible charges, like iron, then I need to figure out the charge, but it's still iron, something. That's the Roman numeral of the charge right there. It goes in the parentheses. And then the polyatomic ion doesn't get an ending change, so it's just nitrate. Now, because I know the polyatomic ion nitrate is a -1, and there are 2 of them, that's a -2 total, so the iron must be +2, so that's what goes in my parentheses. Calcium has a for sure charge because of its position on the periodic table. It's here in the, there it is, +2 column. And then that polyatomic ion is phosphate. Sodium has a for sure charge, and chloride. And then for the one that is molecular, I just say nitrogen. If there was any other number than 1, I would have to say a prefix, but since it's just 1, I don't use a prefix if it's the first element. And then oxygen would be dioxide. All right, now for my compounds where I have the name and I'm going to get the compound, I figure out what the elements are. Lithium and carbonate. Remember, if it's not an IDE ending, it's anything else, then it has to be a polyatomic ion. So carbonate is CO3. And then I can look on the periodic table and see lithium is a +1. And hopefully I remember that carbonate is a -2. So I'm going to need 2 lithiums for every carbonate. Aluminum is a +3. Sulfate is a -2. So to make the charge cancel, I'm going to need 2 aluminums and 3 sulfates. Calcium is a +2. Phosphate is a -3. So I'm going to need 3 calciums and 2 phosphates. I'm just trying to make these charges add up to 0. I'm just being careful not to forget about charges. Don't just write calcium phosphate, right? You have to think about the charges every time. And then copper and bromine. Bromine is a -1. The Roman numeral tells me that copper is a +2, so it must be CuBr2. And then nitrogen, 2 of those. Oxygen, 4 of those, tetroxide. All right, periodic trends. All right, so ionization energy. I know ionization energy is higher if I'm going in the the up-down direction. It's higher as I go toward the top. Ionization energy is how much energy it takes to remove one electron, and the closer that electron is to the nucleus, the harder it will be to remove. It also increases as I go from left to right because these guys over here want to gain an electron. They don't want to give up the electrons that they have. So let's check my periodic table. All right, magnesium and calcium. Magnesium is higher than calcium, so magnesium should have the higher first ionization energy. Calcium and arsenic. Arsenic is further, calcium is here, arsenic is over here in the same row. Arsenic is further to the right, so it should be arsenic. All right, that was ionization energy. Radius increases as I go down. As you add subshells, it gets bigger. But it also decreases as I go to the right or increases as I go to the left because when I add protons, it attracts the electrons a little bit more. And so that's how the trend goes. Okay, so then boron and aluminum. Sorry, right in the glare. Aluminum is lower than boron, so it should be bigger. The smaller radius then would be boron. I have to read this twice to make sure I answer the right question. And then boron and fluorine. Fluorine is to the right. That would be the smaller one. Is that what it asks? Smaller? Yep, so that'd be fluorine. All right, now what about between ions? So now we're not changing the number of protons. We're only changing the number of electrons. Here I took away 3 electrons, so that would make it smaller. Here I added 1 electron, so that would make it bigger, so the original would be smaller. Maybe I should be circling these. A's and B's are confusing here because I've... Okay, there we go. Like here, A means B. Yeah, okay. Anyway. Excuse me. All right, so electron affinity increases. All right, electron affinity. How much does it want an extra electron? It wants an extra electron more as we go this way. And electronegativity Actually, I think that might be in chapter 6 of our book, so maybe that's not on the exam, but electronegativity also increases that way. Yeah, cross that one off. But electron affinity increases from left to right. So in the example of calcium and bromine, bromine would have the higher electron affinity. It has a higher electronegativity as well, but that's actually not in our chapter 5. Sorry about that. Okay, moving on. Almost to the problems, the fun part. Bromine is the only nonmetal that is liquid at room temperature. It's an isotope. All right, how many protons? It has 35. I see that right down here. I also can look on the periodic table. Whoa, sorry. Technological mess over here. 35 protons, always. This does not have a charge written by it, so it's the same number for the electrons. The neutrons is 81 minus, which at the end of the day, I've got to make sure I check my math on these. 46. The mass number is that one on top, 81. All right, now we're to the fun ones, the problems. All right, first up, molar mass. I just want to figure out the mass of each element. Iron is 55.85. And how many I have of it. So 2 times 55.85. Remember, this gets distributed, so 3 times 32.07. And then 12 times, pretty close to 16 exactly. So we'll do 16 for oxygen. All right, 399.91. How many moles of iron 3 sulfate are in 6 grams? All right, 6 grams. I just need to flip my conversion factor so that the grams is on the bottom and divide. 0.015. And let me just be clear that that's the whole thing, because the next question is not about the whole thing. That's how many moles of the whole thing. How many moles of sulfur are in 6 grams of iron sulfate? So in 0.015 moles, sulfur. There are 3 moles of sulfur in 1 mole of the whole thing. So I just have to multiply by 3. And I have 0.045. Now, how many grams of sulfur are in 6 grams? How many grams of just sulfur? So to figure that out, I can use the molar mass of just sulfur and the moles of just sulfur, this number here. All right, so the 0.045 moles So just make sure when you're using a molar mass, it's the molar mass of the thing you're measuring. So up here, I had 6 grams of the whole compound, so I used the molar mass of the whole compound. Now I'm talking about just sulfur, so I'm using moles of the whole of just sulfur, molar mass of just sulfur. And 1.4 grams. How many moles of iron are present in iron cylinder that weighs 25 grams? All right, so this is 25 grams of just iron. So just the iron, molar mass of just iron. Feels easy after the last one, right? When it's just one element, it's simpler. When it's a compound, it's a little more complicated. And the questions I can ask can be a little more complicated. All right, I should have 2 sig figs, so 0.45. All right, consider this many atoms. What is the mass and how many moles? I actually want to do this one first, right? So I need the moles to get the mass, and so I might as well I'm going to start down here. All right, so 7.80 times 10 to the 18th atoms of carbon. And I need Avogadro's number. Remember, that's the conversion between anything I can count, the individual units, and moles. All right, so sorry, there it is. It's pretty small. I'll just go ahead and convert it to scientific notation because it seems a little easier. How many? I want 3 sig figs, so I want 1.30. So the 5 should round that up to the 9 should go up. So it ends up 30 times 10 to the minus 5 moles. And then that is what I can start up here with. The molar mass times the moles .55. And I'm looking at the answer key right now, and it says 1.56 times 10 to the minus 4th. The reason is because I used the whole answer I got here and just put in answer. If I just did 1.3, then I get 1.56. Either one of those would be fine. It just sort of depends on where you round it or what you put in as your starting amount up here. Either answer would be fine. All right, how about wavelength? I need to convert it to frequency. I need to convert it to energy. And then energy in a mole. Okay, so the first thing I'm going to do, I'm just going to do this right off the bat because I'm going to need it. Is convert my wavelength to meters. A couple of things I'll say here. The conversion factor can look different if you get the same answer as me. So 468 divided by 1 times 10 to the 9th, I get 4.68 times 10 to the minus 7th meters. Okay, so if you put 1 times 10 to the minus 9, that's fine, as long as it went with the meters, so you could multiply by that. There are a lot of nanometers in 1 meter. So if I want to put the 1 with the meters, then this would be a big number. Also, this is a visible light, 468. That's right in that 400 to 700 nanometer range. And so any visible light has a wavelength in meters that has 10 to the negative 7th. So if you know that, then you could have that as a second check as well. Okay, so that's my wavelength in meters. To calculate the frequency, I need this equation. V, nu, is the frequency. So I need the speed of light. So nu equals the speed of light, which is 3 times 10 to the 8th meters per second. If you don't remember that, it is on your equation sheet. It has a bunch of extra sig figs. I'm just putting 3 times 10 to the 8th divided by the wavelength, 4.68 times 10 to the minus 7th meters. So this is why I needed to convert it, right? So that the meters would cancel and I can get an answer in hertz. All right, it's getting kind of messy here, but 6.41 times 10 to the 14th. Remember, the units are hertz, or it could be 1 over seconds, or inverse seconds. All of those are the same. Any one of those units would be fine. Energy also has a constant in it, and the constant is also on, there you go, the equation sheet, 6.6. I always read it as 6.626. I think the book says 6.63. Whatever you round it to is fine. And the units are joules times seconds times the frequency, which is what we just figured out. I'll put it as 1 over seconds so that you can see how the seconds cancel, and my units would be joules. 4.25 times 10 to the minus 19th joules. Now that's technically joules per photon, right? That's what this equation gave me. That's what this question asked for. Now it's asking for a mole of photons. Remember that anything can be converted, anything that's small that you can count. There's 6.022 times 10 to the 23rd of those in 1 mole. So I can use this, setting it up with Avogadro's number, so photons cancel, and this would tell me how much energy I have per mole. And I guess, sorry, 2.56 times 10 to the 5th. I see on the answer key it's in kilojoules. Oh yeah, per mole. Kilojoules per mole. So let me just it doesn't if the question does not specify what unit your answer needs to be in, then either one of those would be fine. The answer key just has one. Either one would be fine. Better pile some papers under here so I don't. Okay, I don't want my marker to bleed through all my paper here. All right. 32 fluid ounces can of juice. What is the volume in milliliters? They gave me the conversion factor. Only conversions you should be able to do without a conversion factor are, prefix conversions. Okay, I didn't write my unit. I don't want to do that. There we go. Fluid ounce. Ay, ay, ay. All right, now I can put 1 fluid ounce down here, 29.6 milliliters on top, and that says I should multiply. Going back to my data, I have 3 sig figs, so it should really just be 947 milliliters. Convert it to liters. I just divide by 1,000, remove the decimal 3 places to the left, and I get 0.947 liters. All right, write this number to 3 significant figures and scientific notation. So scientific notation, I just need to move it 1 place. So it would be times 10 to the 1. And it'd be 5.2, and then the 0 would be the last one. It should go up. So 5.21 times 10 to the 1 is my 3 sig figs. Density. Okay, density equals mass times volume. I'm going to be solving for volume, so I need that to be by itself, and I need it to be on top. So you could do, whatever way you want to get that on top. I'm going to cross multiply. So density times volume equals mass. Then I'm going to get it by itself. So volume equals mass over density. I have those things. .3 divided by 0.988. I should get 3 sig figs, so 14.5 is my answer. The grams cancel, and now I have centimeters cubed in the denominator of the denominator, which is the numerator, so that's it. That's my unit, which is a volume unit. All right, and last but not least, percent composition. So for percent composition, I need to figure out the molar mass of the whole thing first. So let me just go ahead and do that. I'm just going to do it in my calculator. So 12 is the molar mass of carbon, and there are 20 of those. 1 is the molar mass of hydrogen, and there are 24 of those. 14 is the molar mass of nitrogen, and there are 2 of those. And 16 is the molar mass of oxygen, and there are 2 of those. So 324 grams per mole. For each element, then, I just say how many I have times the molar mass of that element divided by the molar mass of the whole thing times 100. I'm going to write them all out, and then I'll put them all in my calculator. So hydrogen, 24 of those, times 1. Nitrogen is 2 times 14. And oxygen, 2 times 16. All right, now I can just put them all in my calculator. So 20 times 12 divided by 324. There we go, 70.74. I need to multiply by 100 to make it a percent, or I could just do that in my head. So 74.07%. .24 times 1 divided by 324 would be 7.4%. 7.41%. I'm just going to do 2 decimal places because that's what my molar masses typically have. I did round some of them. This one should probably be like 12.01, but I'm going to leave 2 decimal places. 2 times 14. And again, I'm just doing the multiplying by 100 by moving the decimal places 2 places to the right in my head, so 8.64%. And 9.88%. And I can check my work. I mean, it won't give me 100%, tell me if I got it right, but I can check by adding them all up and making sure they add to 100. And they come out to 100. All right, that's it. Good luck on exam 1.